My name is Natasha Batalha. I am a research scientist at NASA Ames, and I was tasked with presenting a talk on spectroscopy of exoplanet atmospheres for this year's 2020 Sagan Summer School. I'll be discussing exoplanet atmospheres from the perspective of writing a proposal to obtain atmospheric spectroscopy data from either the James Webb Space Telescope or the Hubble Space Telescope. So I'm going to focus on three aspects: target selection, modeling, and the statistical analysis. So by target selection, I mean what accuracy in planet properties do we need before we can go and get atmospheric follow-up in the first place. By modeling, I mean what tools are available to determine what spectral precision can be obtained on an atmosphere with JWST, and to determine the approximate atmospheric signals of these planets. And lastly, by statistical analysis, I mean how can you prove to a time allocation committee, of course, that a certain planet's atmosphere is in fact detectable. And I'll add that this entire analysis and tutorial is available on GitHub. The link is here at the top, so if you want to follow along, I would head there, clone the repository, and then come back when you have the Jupyter notebook open and ready to go so you can follow along. So the very first aspect of spectroscopy proposal writing is, of course, what the EPRV community is doing, and that is determining planet properties. There is a tension that exists between the detection of a new planet with, let's say, TESS, and the follow-up observations that we want to obtain with HST or JWST. We'd hope, of course, this would be a super seamless pipeline, but in reality, extensive RV or TTV analysis must be conducted to get a mass first. And then, and only then, if a target is deemed to be a good one, can we proceed with atmospheric follow-up. Of course, this naturally begs the question of, to what level of precision, if any at all, do mass measurements need to be for a robust retrieval of atmospheric properties? And I say if any at all because the transmission spectrum is related to, of course, radius, gravity, temperature, mean molecular weight, which describes how heavy the atmosphere is, the concentration of all the gases, which is this parameter psi, and then these sigmas, which are the gas and the cloud cross-sections. Now, because of this gravity dependence in Z, it has been postulated that you could retrieve gravity as a free parameter and subvert time-intensive radial velocity altogether. The problem is that there are two parameters in this function that are largely degenerate with each other. That is mu, the weight of the atmosphere, the mean molecular weight of the atmosphere, and g, the gravity. For gas giants, we can pretty much assume they consist of primordial hydrogen-helium atmospheres and that their mean molecular weights are roughly around 2. But for small planets, we cannot make that same assumption, and so these two parameters become highly degenerate. So here I am showing two spectra. Here are two very different planet cases. One is rich in water with a low gravity, and the other is sparse in water with a high gravity. And their spectra are observationally identical. So mass is definitely needed to correctly determine the composition, but we still don't know how well or if the level of precision needed varies as a function of, let's say, planet size. So here I'm showing the 1 sigma mass uncertainty for targets available on the NEXI database. And you can see that many targets have relatively high mass uncertainties, even some of our gas giants. In order to answer these questions, you can do a simple exercise and select a rough population of planets spanning your parameter space of interest. Here, we chose a range of planets spanning hot Jupiters to sub-Neptunes all the way down to TRAPPIST-1e, which is a more temperate terrestrial planet. We also made sure to span cases that covered several different atmospheric compositions and cloud parameters, so that we could track down, of course, as best we could, this question of what mass precision was needed over such a wide parameter space. We then ran a Bayesian retrieval analysis to determine where the constraints on the atmospheric parameters when the prior and the, what were the constraints on the atmospheric parameters when the prior on the mass was very large, as in the mass was not known at all. Then we slowly increased the precision on the mass until the posteriors of the atmospheric properties approached that of when the mass was known infinitely well. And in doing so, we tracked both the accuracy and the precision of the posteriors in terms of how much they were degrading. So here are the first sets of results for the case of WAS-17, HAT-P1b, WAS-12b, HAT-P26. These are hot Jupiter, warm Neptune cases. And I've taken some artistic liberty to animate these posteriors. But what you can see is for these larger gas giant planets, the retrieved precision and accuracy of the atmospheric parameters did not largely depend on whether or not mass was known. Because remember, we have a good idea of what the mean molecular weight is. There was, however, a slight degeneracy between the reference radius and the mass, as you might expect, as they're related through the gravity. And then lastly, for the case of HAT-P26, which had a slightly enhanced metallicity of 4 times solar, you can see that the accuracy and the precision on the mass itself was degraded compared to its 1 times solar metallicity counterparts. And this is foreshadowing to the fact that the enhanced metallicity is going to be problematic in attempting to retrieve physical properties when the gravity is unknown or when the mass is completely unknown. Okay, so the next case I'll show is of GJ1214b, the famously flat planet, which has a very high metallicity and a very high cloud deck. And this will sort of exemplify what happens on the other end of the spectrum. So for this case, as the precision on mass degrades, the posteriors of both metallicity and temperature drastically lose both precision and accuracy. And in fact, the atmospheric properties can only be inferred with a mass precision of better than 50%. But even at that level, the widths of the posterior distributions are dominated by the uncertainties in mass. So then, if you improve your mass to 20%, the widths of the posteriors finally become dominated by the spectroscopic data quality and not by the unknown mass, which means that ultimately we need at least 50% masses for initial characterization, but we should really be aiming for 20% masses if we want the posteriors to be completely dominated by only the spectroscopic data quality. So if you're following along the tutorial online, you've learned how to use the Exoplanet Archive API to query confirmed targets and also transform them into usable formats. You also now understand why I've only taken those targets with better than 20% precision. The last thing you'll see that I did is one additional cut to remove anything that was dimmer than J of 12-ish. And we are moving a little bit ahead of ourselves at this point, as we haven't yet talked about obtaining JWST instrument precision measurements yet, but when you are looking for targets, I think it's super important to have an intuition for what approximate precision, some stellar magnitude is going to give you. So here are 4 JWST spectroscopic modes, all sampled at R of 100. On the y-axis, I have the single transit spectral precision in parts per million. On the x-axis, I have J magnitude. And for some initial context, hot Jupiters tend to have spectral features in the hundreds-ish of ppm. This is a really rough cut, but it's just to give you an idea. And terrestrial planets have spectral features in the tens of ppm. So at J of 12, you're kind of already pushing the limit of what spectral precision you need to do a hot Jupiter spectrum with one or so transits. And that's why I went ahead and queried for only those stellar hosts with magnitudes brighter than 12. Now that we have a good target list in hand, we'll focus on what tools you need to really start determining the atmospheric observability of these targets. We're going to assume for this exercise you already have a target in mind. For atmospheric studies, when you are determining your science goals and hypotheses, the first thing you have to decide is where you sit on this, where you sit in this hierarchy of science goal complexity. The level of complexity you can attain usually has to do with how strong your atmospheric signal is. Remember, terrestrial planets were somewhere in the tens of ppm and hot Jupiters were somewhere in the hundreds of ppm. And this follows along with what we've seen with the Hubble Space Telescope analyses. For example, Julian DeWitt's atmospheric reconnaissance of the habitable zone TRAPPIST planets fell squarely into the can we detect an atmosphere category. On the other hand, Hannah Wakeford's analysis on HAT P26b, which had a very prominent spectral feature, aimed to get very well-constrained abundances, temperatures, and cloud information. Now, before any of these programs were awarded time, these groups had to determine the observability of their target of interest, which again just equates to figuring out where you fall in this hierarchy. So the big questions become, what is the process for doing this? And of course, what tools do we need? Before we do anything, the first step is to familiarize yourself with the available observing modes, their resolutions, and their wavelengths. For this talk, I'm only going to be focusing on the bright object time series, or the BOTS spectroscopy modes, which I'm showing here. The 4 instruments cover wavelength regions from just short of 1 micron all the way up to 14 microns at resolutions ranging from 100 to a few thousand. And I'm also putting a bar down here for the James Webb Telescope user documentation, or JDocs, which has a load of information on all of these different observing modes. So the very first calculation we will do is select one observing mode from each of these instruments such that we cover the entire wavelength parameter space. And again, you can follow along with these tutorials if you are interested online. Here we've picked GJ436b, and we've set a constant transit depth spectrum. And this allows us to use the same Pandexio calculations throughout our modeling. And so with this, we can get an initial idea for what the precision is across wavelength space for all our different modes. So let's look at this precision plot a bit more in depth. So the reference people usually use for sort of gold standard precision is the 20 to 50 ppm noise floor that was cited in Tom Green's 2016 paper. So we can immediately see that this target has potential for atmospheric success. Of course, the big question mark is still what the atmospheric signal actually is, and this is where the radiative transfer models really come into play. Currently, there are lots of radiative transfer tools available online. These tools cover everything from transmission spectroscopy to emission spectroscopy to reflected light. Here on the side, I'm showing a little present symbol, which indicates that the tool is open source, and the running girl indicates if the tool is pre-packaged with something like MCMC or multi-nest so that it can be run quickly to retrieve atmospheric parameters. For this demo, I'm going to work with Chimera and Picasso. Between the two of them, they cover all three observing geometries, so transmission, emission, and reflected light. But I really do encourage everyone to check out all the open source tools available if you are interested. You should also be able to reproduce the statistical analysis that I did with any of these other open source tools, especially if you already have a favorite that's already installed and ready to go. So starting with transmission, we're going to use Chimera. We are going to run the simplest, most optimistic case, which is that of cloud-free solar metallicity, solar C/O. Now, the reason this helps us a lot is if you remember our initial equation, when we assume cloud-free, we automatically knock out one of these parameters. Then, if you remember that that psi parameter, which represents the abundances of all of our atmospheric gases, if we instead assume chemical equilibrium, we can replace this with a function that is dependent on pressure, temperature, C/O, and metallicity, which automatically reduces our number of parameters tremendously. Now, the only thing we have left is the temperature pressure profile, which we are going to parameterize using the planet's equilibrium temperature. And now we have all of our model parameters sort of taken care of for an initial pass. Another thing to note is that these assumptions aren't just to make our lives easier. They're also grounded in the kinds of planetary science questions we want to answer. For example, we'd like to understand bulk exoplanet properties via correlations with things like mass. So here I'm showing the recently updated mass metallicity plot that shows currently measured metallicities of exoplanets against the metallicities of the solar system objects, which do follow this nice correlation with mass. So with that, we have our very first nice spectrum. I'm shading in our approximate error bars that we got from Pandexo runs in the first exercise. And you can see that this looks awesome. But we have to check ourselves. For any target you wish to observe, it is incredibly important to check what data might already exist. And you can do this on ExoMast. The link is in the tutorial. In the case of GJ436, the data is available. And if we grab it and plot it against our model, we'll see that things just don't match up too well. And herein lies the very first lesson, which is proposals with one-time solar cloud-free claims are often, or pretty much all the time, far too optimistic, especially for something like GJ436. However, the size of the spectral feature does give us a nice upper limit on our original precision plot. And while this is progress, this range is still really large. So the question becomes, how do we increase our realism from this point? Well, the first thing you can do is go back to our mass metallicity plot and try and grab the corresponding metallicity given the mass of your planet. Doing this will bring you much closer already to what the data actually shows. So now going back to our hierarchical science goal complexity list, we can pretty confidently say that a detection is within possibility. But unfortunately, we're not done yet. There are still two questions that we need to answer. The first is, at what significance can the detection be made? And the next is probably the biggest looming question of all, what about clouds? Now, before we address these questions, I want to stop and point out that in the online version of the tutorial, we repeat what we've done so far, but with emission spectroscopy using the Picasso radiative transfer tool. But because up until this point, the procedure for both is virtually identical, I'm going to leave it up to you to follow along there and do the runs, and just in the interest of time. Okay, great. So we've deemed what accuracy and planet properties we need. We've looked at some initial tools and determined the procedure for running those codes. Now, finally, we can address our last question of how to actually prove observability. And there are many strategies to do this. What I'm offering here is just an initial methodology to get you started thinking along the lines of being an atmospheric observer and kind of what goes into the sauce. So again, returning to our two questions, the first thing to realize is that for transmission spectroscopy, this question of can we detect an atmosphere really just translates to can a y equals mx plus b model be rejected by the data? If you think about planets or observations like TRAPPIST or JJ1214, this was ultimately not the case. The y equals mxb model could not be rejected. Now, doing this test is incredibly easy, so it doesn't hurt us to cover a good amount of parameter space when doing the analysis. So in the tutorial, I loop through 3 different cloud cross-sectional strengths and 4 different metallicities. And the last thing you'll, of course, want to loop through is the different instruments, because the answer, of course, is going to vary for every observational setup. So here are the results of that analysis, which are again in the GitHub notebook. The whole analysis takes less than a minute or so to run. And not only are we proving whether or not a scenario is observable, but we are also getting a sense for what observing modes are best for doing this atmospheric detection in the first place. So here you can see each little box for different cloud cross-sectional strengths and different metallicities, and I've colored everything based on whether it can, the y equals mx plus b model can be strongly rejected, whether it was just a weak rejection, or whether you could not reject it at all. So you can see that that MIRI there are only 3 cases where a strong rejection of the flat line can be achieved. For nearest sauce, it's the same story. And although NearCam and NearSpec are semi-comparable, NearSpec pulls ahead slightly due to its larger wavelength coverage. Now, we'd also like to repeat the same exercise for the emission spectra. The number one difference between these two analyses, though, is emission spectra are less susceptible to obscured features from clouds. And instead, one of the 0th order effects on emission spectra from a modeling perspective is your choice of temperature pressure profile, of course, because of sigma t to the 4th. The second major difference is instead of ruling out a y equals mx plus b model, we're going to instead roll out a simple black body. And now everything else pretty much remains the same. We'll loop through, instead of clouds, temperature perturbations from equilibrium, using equilibrium as a starting point, then metallicity again, and then, of course, the observing mode again. In this case, here you're looking at the same type of plot as we had before for transmission. In this case, of course, NEAREST just doesn't have the wavelength coverage to see emission, as the wavelengths are too short. MIRI LRS, surprisingly, also suffers a bit as compared to NearCam and NearSpec, which come out nearly identical. At that point, in deciding between these two modes, NearCam and NearSpec, there are other factors that you might want to consider choosing. This could be things like resolution or even just wavelength coverage. And with that, we've fully answered the first question of whether or not the atmosphere can be detected. The next part of the tutorial is assessing how to detect a certain molecular feature. So this could be, for example, if you just wanted to hone in on being able to detect methane in some spectra amongst other absorbers. The simple way of doing this, which I show in the tutorial more rigorously, is to remove that singular opacity contribution from each model. And that will leave you with two models, one with and one without the parameter of interest. And that way you can reproduce the same exact statistical analysis that we did with the flat line or the black body rejection. Now, the very last part of this tutorial will be trying to determine if you can actually constrain something with your planet of interest. There are primarily three ways of doing this, and there is by no means a clear-cut way to determine, which one to use, which one is best to use. My rough recommendation looks something like this. If you have a large model grid that is available to you with your relevant physical and planet properties, then a grid search will do just fine. The benefit here is that you won't have to do any extra modeling. Unfortunately, many times grids are just unavailable for your parameter space, for your particular parameter space, especially for new proposal ideas, and that may push you to using other methods. So if you don't have a grid, the next question to ask yourself is if you are worried about non-Gaussian posteriors. So this could be things like degenerate solutions or being able to achieve upper limits, to only achieve upper limits. If you're not worried about those things, then information content theory is usually the way to go. It's super fast and requires very few model evaluations. Now, if you neither have a grid or the IC is not going to work for you, then retrievals might be the way to go. The pro is, of course, that it'll capture any of those funky posteriors. The con, and also the big reason I tend not to start with retrievals, is that they're just slow. And this is especially cumbersome for proposals where, like we've seen so far, we often just want to do many test runs across a load of parameter space. So for this tutorial, I decided to go with information content for a few reasons. First and foremost, it's fast, so it can be contained easily within a notebook. Second, there exists already many in-depth tutorials on retrieval analyses specifically for atmospheric observations and transmission and emission. So I encourage you to check both of them out, and the links will also be in the tutorial for those. In general, though, the information content theory just seemed like the biggest gap in what's currently available, and so that's what's included in the tutorial. So the first step of IC is to compute the Jacobian. The Jacobian describes how sensitive our model is to slight perturbations in each state vector parameter at each wavelength place. The next step is to build the prior matrix. Because the information content describes how your state of knowledge has increased relative to the prior, it's critical this gets defined. And in most cases, there just is no information, as in we know nothing about the system beforehand. So we want to make these very large. The last step is to build the error covariance matrix, which describes the precision of your measurement on each wavelength. So these we can take directly from Pandexo, so we don't have to do any additional work except for to put it in matrix form. And now that we have all those three, we can start computing useful and fun statistics. So I talk about a few different statistics in the tutorial, but the two that I'll highlight here are the posterior covariance matrix and the information content. So the diagonal elements of the posterior covariance matrix give us basically the 1 sigma constraint interval on our parameters of interest. And you'll be able to tell right away if a constraint is possible if this number is significantly smaller than the prior value that you assumed. In the case of our tutorial, our prior value was 6 orders of magnitude. So here we have a really nice constraint on our parameters of interest. The other helpful statistic is the information content, of course. The IC is a single value, it's measured in bits, that encapsulates the total information gained from the observation. So this parameter is incredibly useful in comparing various modes head to head. Here, the figure the little GIF that you're seeing, that you're looking at, is an IC heat map that Mike Klein and I used in our paper to determine what combination of JWST modes were most optimal. So you can see that you can use these statistics in 1,000 different ways to test various combinations of observational strategies until you find one that really suits your needs. My final thought is that after all this analysis, you can always create what I'm calling no signal scenarios. You can always push that cloud deck higher or crank up that metallicity. The important thing is to be explicit and consistent in explaining where you stand in this hierarchy and for what parameter space or in what parameter space. And with that, we've covered what accuracy and planet properties we need, what tools exist and how do we use them, and ultimately how we can prove observability to write transiting atmosphere proposals. And I thank you for sticking it out to the end with me. If there's anything that was unclear about the tutorial, feel free to add issues and submit pull requests to the GitHub. I'd be very happy to get feedback and improve upon what I've initially built so far. Thank you.